All right, this is where we left off yesterday. So, one of the things that we need to kind of focus on is the change in physical states. Yeah, their point's off, by the way. Okay. All right. So we need to talk about physical changes because that's what we kind of focused on on yesterday, and we need to understand how differing physical states of matter have differing enthalpy and entropy changes, and that's one of the key parts we're going to talk about. So, number one, the greater the disorder, the greater the entropy. You already know that. So, the more chaos you have going on, the higher the delta S value. The entropy increases as substances entropy increases as things change from solids to liquids to gas. You already know that. Number three, when a pure solid or liquid dissolves in a solvent. Now, what would that be creating? Very good. So this right here creates, we change the color to blue, so it creates aqueous solutions. Read them what it says. When you take something and you dissolve it into its ions or into its particles, does it become more disordered or less disordered? More disordered. So that is going to increase in your entropy. Now read that in white. Carbonates are an exceptions. They interact with water and actually bring more order to this system. Now, I'm about 99.99% sure they'll never ask you, what is the exception to the entropy rule for dissolving of solids? They're not going to ask you that, okay? How much? 8? Okay, I'll write a check later. Thank you. It's extra, right? Okay. Yes, and that's the thing. Yes. All right, so here's my first question. Listen. If I've got two different solutions, one of them is silver nitrate, one of them is sodium chloride. First of all, how do you know that silver nitrate's 100% soluble? Okay, the nitrate. Sodium chloride, how do you know it's 100% soluble? Group 1. So here's the deal. So this is what Jake was talking about. What happens if we pour these two things together? What would form down here in the bottom? What precipitate? Very good. So you've got silver chloride that's actually going to form down here in the bottom. So if you were to mix two solutions and cause a precipitate, is that becoming more ordered or more disordered? More ordered. Stop. But let me finish this thought. And here's the situation that a lot of students mess up. You all agree that it's becoming more ordered. But here is the trickiest question to all of it. What is the sign of delta S then becoming? Very good. That is the number one most missed part of entropy, is that when things are actually coming together to form more perfect systems, it's actually a negative value, not a positive value. And so that's one of those mental things that I can't help you. All you have to do is you've got to put the time and the effort into doing that. Okay, so what were you? Go ahead. I know that, but it's one of those things like you just kind of roll through it and you don't stop and say, wait a minute, hold on. Let me think about the process that's going on. Yes. All right, what were we saying? Yes. Yes. And when you dissolve them, for some reason, they form some other type of more structured environment. So they precipitate. A solid precipitate. Potentially, depends on what you're mixing. Yeah. Okay. Okay, y'all stop. Okay. Now, when a gas escapes from a solvent, the entropy also increases. Can I give you a perfect example, number 4? What if you shake up a Dr. Pepper and then release and then open it up? That's exactly what's happening in number 4. What is specifically the gas molecule escaping from a solvent? And it's carbon dioxide that's leaving the liquid, right? So that's what carbonation is. Entropy generally increasing and increasing molecular complexity. Put a big star beside number 5. That's the one that a lot of students forget about. What in the world does it mean by increasing molecular complexity? A larger, crystal is more complex. And there's one key reason, and it's down here in this part right here. That white phrase. So if you're highlighting, I would highlight that part right there. Moving electrons. And here's the deal. Let me give you an example, and I've used this example a lot. If I take you up the street to Slingla, and I send you outside with 5 kindergartners, is it possible to manage? Well, what happens when I let out the other 15 in that class? Okay, things change. It becomes a lot more chaotic very quickly. So when you add more atoms, do you add more electrons? Yes. What happens when you add bigger atoms? It's even more electrons, right? So let me give you an example. There's 2 ways to look at it. It gives you this one. I do believe, and help me out, the example that they gave was KCl versus CaCl2. Is that correct? So this one, first of all, my question is, which one will have more electrons? All right, so you've got 70 here, and calcium is, what, 20? Yeah. No, why did I say 70? That's not right. The mass would be 70. Cl, 17 times 2, my bad. 17 times 2. So you're going to have a total of there, which is some number, and then over here, what? 54 total? Okay. All right, so you got 54 total here. Again, chlorine is not, I keep wanting to do the masses, not the number. So 17, and potassium is 19, so you've got 26. All right? 36. I forgot to carry the one. So you've got 36. So this one is going to be a lot more entropic than the one on the left because it has more electrons. But what happens when you do a comparative of where you have Kf versus Ki? You have the same number of atoms in each one of them, but what do we know about I versus F? That's true. No, because of the number of things moving all at once. It's a prime example. Let's say you have 20 kindergartners and you have 20 fifth graders. Which one will be harder to control? You think so? Fifth graders are a little pain in the butt. They're very deceiving. They're the ones that will climb over the fence. Okay. And they're going to be like pushing people down and beating people up. Like kindergartners don't really do that. Okay. So the larger the atom, the more chaos you're going to have. All right. Finally, reactions increasing the number of moles of particles often increase in entropy in general. The greater the number of arrangements, the higher the entropy of a system. And that's kind of what we were talking about yesterday. You've already seen this. As the order increases, delta S goes down. As the disorder increases, delta S goes up. You already know all that, so we're good there. We've already talked about that. So these are spontaneous physical and chemical processes. Now notice, these are physical and chemical. So the first one, waterfall runs downhill. Physical. But let me ask you something. Could it possibly run uphill? But what would nature have to do? Supplied a lot of energy, which nature's not going to do. All right, a lump of sugar dissolves in a cup of coffee. It's physical because it's turning from a solid clump and it's dissolving into smaller particles. But did the sugar chemically change itself? No, okay? At 1 atm, water freezes below 0 and ice melts above 0. That's physical changes. And again, those are all things that are true. Heat flows from a hotter object to a cooler object. That's true. A gas expands in an evacuated bulb. That's also true. And then iron exposed to oxygen and water forms rust. That's a chemical change. Go ahead. Okay. So, in the skier example, which is over here in the picture to the right, which takes more energy? The guy in the red coat or the guy in the purple coat? Why? He's going up. But why does that take more energy? Okay, so is that a spontaneous process or a non-spontaneous process? That's non-spontaneous. If you can ski uphill, I would love to see it. That's an amazing feat. So, what would be the sign of delta G? What would be the sign of delta G in the red coat? Why negative? Because that's spontaneous. That's thermodynamically favorable. So, you've got to remember this. Does the skier have work being put into those skis going down the hill? Yes, he's working, but he's not using all of it, right? But what happens to the guy in the purple coat? He has a certain amount of energy, but does he have enough to get him back up the hill? He's going to need some extra, right? It's not going to be whatever he has to be able to do it. Okay, so predict the sign of entropy change for the following process. Again, so it's either positive delta S or negative delta S. See if you can do those two real quick. It's either positive or negative delta S. That's the answer to that question. Print it out and let's see what it looks like. First of all, hang on one second. All right, so Mary, what'd you get for A? Mary for Brady. Solid sugar is added to water to form a solution. Why is it positive? Hang on. We didn't have this problem yesterday. Exactly. It's been nice 2 days. All right, Mary. What'd you say? Why'd you say it was positive? Okay, but what does that have to do with anything with delta S? It's separating into farther particles. That's the part where I want you to kind of explain that. All right, Devin, iodine vapor condenses on a cold surface to form crystals. Is it becoming more ordered or more disordered? More ordered. So what is that? That's negative. And I told y'all 2 minutes ago, but Peyton reassured me that no, that's really easy. I'm just saying, I'm telling you, this is a difficult part for most people. You have to think about it backwards. Now, let me ask you something real quick. If you had to name the process occurring here, what is the name of the process that occurred? Crystallization or an S word? This is solidification. This is going from a gas right into a solid, okay? All right, so which of the following, and this would be a prime example of a multiple choice style question that you would see on a test. And I want you to answer this. Don't say it out loud, just circle it. Which of the following has the largest increase in entropy? Just circle the correct answer. Wish it was as clear as this. Go back in and add tiebreaker underneath that if you don't mind. All right, Cody, what'd you get? Okay. All right, so let's talk about what that is first. And again, and I'm not saying you're right or wrong. Logan, what'd you put for the answer to this question? You don't have anything? Okay. Do you need to go to the bathroom? Go ahead. Colby? Okay. All right. Brianna, Brian, what'd you put? A. Chase Pulford, what'd you put? A. All right. So, largest increase. So, is this the most disorder or the most order? All right. So, we're trying to create the most disorder. Very good. All right. So we're trying to make delta S positive here. All right. So A, we're going from a solid to a gas. In terms of states of matter, is that very disorderly? Yes. All right. We're going from gas to gas to gas. But remember, when we talk about different states of matter, there's one thing that you have to incorporate. You've seen this, but you probably forgot. How many moles of a gas did you have on the reactant side? 2 moles of a gas. So you went from 2 moles of a gas to 2 moles of a gas. So how much entropy change did you even have? You didn't even have an entropy change here. So B is automatically out. You go from a solid to a liquid. Now, is solid to liquid as much disorder as a solid to a gas? No, so we can also get rid of C. And then D, we're going from diamond to graphite. What state of matter are both of those? Solid. So we're going from something that's solid to something that's also solid. So is there as much change? No. So A is your correct answer. And that's actually a really good question. I would still say no because it's still in the solid state of frame. Because you're going from a solid to a gas, that's taking something that's really close and you're just shredding it everywhere. So restate your question then. So diamond to graphite is becoming more disordered because of the molecular complexity. Diamond's more molecular complex because of how it's a network covalent versus just a covalent bond. It is becoming more disordered, but not as much as solid to gas, because the question, which one has the largest increase? So it is becoming more disordered, but just not as much. Just like C is becoming more disordered, just not as much. Go ahead. Actually, this is a spontaneous process. It is. The diamond to graphite actually has a negative delta G, which means, ladies, your diamonds will eventually turn into pencil lead. It's a natural process. And here's why. How are diamonds formed? Compressed, which is a non-spontaneous process. So over time, it actually it falls back apart. No, y'all will all be dead in dust and bones before that ever occurs. Yes, but you don't have enough temperature or pressure that we can create to make that happen. I mean, you can. I don't know of a lab that does it, but you can research it. You can. I mean, I would start with coal before I would start with graphite because coal is closer to diamond than graphite. There is one, and I think it's one of those two. Yeah, yeah. All right. So here's my question, guys. Stay with me. Remember how we talked about there's 5 different ways to calculate delta H. We said there was Hess's law. We said there was calorimetry. We said there was bond energies. We said there was stoichiometry, and there was another one. Yeah, and tables. Okay, table logic. So here's the deal. There's the exact same ways to solve for delta S, except calorimetry is not involved in that. So you can actually solve for delta S almost the exact same ways. You can use stoichiometry. You can use table logic. You can Hess's law. No, there's no bond energies as well. So there's only 3. And so this is what we're fixing to look at is in terms of trying to calculate delta S. So the question is in blue. What is the standard entropy change for the following reaction? Now, first of all, whose law does this remind you of? Hess's law. Now, the question that I asked you yesterday, whenever you're solving Hess's law for delta H, can one of the compounds in the reaction be 0 for delta H? Yes. When is delta H for a compound 0? When it's in its standard natural normal state. Now here's the question I asked you yesterday. Can delta S in a compound ever be 0? No. Why? When I told you there was 2 reasons, Devin, what were they? And there's no such thing as a perfect crystal at absolute 0. So delta S will never be 0. If and only if this were Hess's law, would any of these 3 species be 0? Oxygen would be 0. But because we're dealing with delta S, can any of them be 0? No. So the math is the exact same. It's adding one more piece of complexity to it because you're not going to have any zeros to eliminate some of the parts of the math. So here would be your numbers. Carbon monoxide has a delta S of 198-ish. Oxygen is 205. And carbon dioxide is 213. So again, but the important thing about this is when you're setting up Hess's law, let me ask you something. What is the lowercase c, the lowercase d, the lowercase a, and the lowercase b? Those are coefficients. So do the coefficients still matter when we're doing Hess's law for delta S? Yes. Exact same math, just a little bit more complicated because you're not going to have any zeros in it. Okay? So did I leave a blank out on this one? I think you actually have to write the answer in. Okay, so go ahead and write the answer in. The answer would be negative 173.6. And I want to add some stipulations to this. So my question to you is nature excited about that number? No. Why is nature not excited about this? Okay, so do me a favor. Underneath that green negative 173, please write the term more ordered. More ordered. This is not okay by nature. Now, in terms of just looking at the reaction overall, can you tell that it's becoming more ordered? What are your states of matter? All of them. They're all gases, but going from a gas to a gas should not matter. That should be, everything should stay the same. But you've got to remember, how many moles of reactant gas do you have? 3. And how did I get 3? 2 plus 1. And how many moles of a gas product do you have? 2. So you started with 3 moles of a gas and ended with how many moles? 2 moles. So is that more or less ordered? That's more ordered. Okay. That's a very good question. I don't know this off the top of my head specifically, but I think if that were the case, it would have to be 0. Delta S would be, as delta S of the reaction would be 0. Not the compound, the reaction. We'll have to look at it specifically. I don't know exactly what part you're referring to. Okay. All right, so again, why are there no zeros? We're going to talk about this. So you should be able to do this. See if you can calculate this particular change in reaction. Real quick, just throwing this at you. Simply based on the reaction and how it looks, is it going to be a positive S or a negative S? Negative. You're going from 3 moles of a gas to 2 moles of a gas. Same concept. So again, plug them in, see what you get. Been talking to Sarah this whole time, so no. All right, so this is what you have in terms of the reaction. So we've got 2 sulfur dioxides plus oxygen gas yields 2 sulfur trioxides. And all I did was rewrite it in terms of delta S of Hess's law. And so then you can just take the numbers and plug them in. So I will need your help on that because I can't see them. So what was the sulfur trioxide value? Is it positive or negative? Positive 256 point what? Okay, thank you. Minus 2 times, and what was SO2? 248.1 plus O2, which was what? 205.3. So when you do all of the calculations, anybody get an answer yet? All right, so negative 188. Now, I'm going to stop there just for, well, all the tables have 4 sig figs, so let's go with that. So negative 183. So here's the thing that I want to point out to you, is that whenever you did this, if you notice, and again, I'll promise I'll come right back to this, the table, let the table, and I think there's a problem with this. There's 2 temperature units and there shouldn't be. It's Kelvin. Let's just leave it at Kelvin. I don't know why that's a typo. So what we're going to do is we're going to come back over here, and we're going to say that this is joules over Kelvin times mole. Is that what it gives you up there? My bad. Well, it says in joule per Kelvin. Yes. Obviously, if this is like an AP question, it'll be correct. So this is the correct answer. Now, when the first thing I asked you in the question was to predict the sign of delta S, and you predicted negative. Did it turn out negative? Yes. Okay. So is nature excited about this? No, it does not like this at all. Don't feel bad. I do too. Everybody got this? When you feel sick, you just want to eat, don't you? Yes. Yeah. Now, this is when things are going to get a little bit odd, a little bit strange. The entropy changes for reversed phase changes. Now, again, phase changes. When we talk about phase changes, what are we referring to specifically? Physical changes. Okay, we're talking about states of matter. So we're talking about physical. Now, every year I contemplate whether leaving this part in or taking it completely out, because I've never seen a direct question based off of this. But at the same time, I think it's important for you to understand one key part about this. And here's what it is. And let me show you this particular thing. So if we have this formula right here. Remember I told you, you already know two ways to calculate delta G. You told me there was negative in Fay, you told me there was negative Rattling, and then I taught you another one. It's that cool phrase. What was the other delta G? Ghetto homies take speed, right? So delta G is equal to delta H minus T delta S. So here's the deal. So if we're talking about at phase changes, I need you to understand something. This is at equilibrium. By this point in your career in this class, as soon as I say that word, something up there needs to be changing in your brain. When we were at equilibrium, remember, what are the three letters that tell us true spontaneity? What does nature prefer this to be? G is, E is, and K is. But when we were at equilibrium, what was G? 0. When a battery is dead, what was your cell potential? 0. Well, think about this. If you take delta G equals negative in Fay, and your battery is dead, you just told me E was what? Well, then what the heck does delta G automatically become? 0. So here's the key concept. If we're at equilibrium, delta G equals delta H minus T delta S. And again, one more time, at equilibrium, then this then becomes true. True or false? True. Not necessarily. And again, we're referring to phase changes. And phase changes occur when? At equilibrium. So here's the next little part about this. What if I don't like this 0 plugged into this formula? So I'm going to change pages. Again, I've got 0 equals delta H minus T delta S. Can I get rid of this 0? What can I do? So in your brain, see if you can come up with this. How did I get that? Why did I didn't mean to pull this negative down. That's a typo. My bad. That's a typo. So, all I did was I added T delta S to 0, which would give me what? Okay, does that help now? Alright, so what I have now is this formula. The whole reason I wanted to show you this was because when I came back to this will now make sense. Delta S is equivalent to plus or minus delta H over T. So now do you see where that formula came from? You are at equilibrium during a phase change. And so what I needed to show you was connecting this to that. Now, here's the question that I now have. Where in the world does that come from? Perfect, Devin. That's exactly right. Delta H can be positive or negative based on what two factors? Exothermic or endothermic. Okay? So what we can determine is based on the enthalpy change of a physical change, you can then determine the entropy change or vice versa. So give the signs to delta H following exo and endothermic guidelines. So you may have read it, you may have cheated, but hopefully you didn't even read that. But it's in there. So these are things that you should know, but we're just stating them out loud. If a reaction is exothermic, the entropy of a system increases. Why does that make sense? So releasing a bunch of energy, what's it going to do to all those particles? It's going to send them everywhere. It's going to push them everywhere. We go to the gas station and light a match, you're going to know it. What's wrong? Why not? I know, I like that one too. Okay. Yes, ma'am. Yes, ma'am. Increases. It also increases the surroundings, yes. Yeah. Yeah. Okay. Yeah. We'll talk about it later. Stop. Stop. Just put it up. Now, here's my question. If it says for mercury, the enthalpy of vaporization. So here's my first question. The enthalpy, first of all, what is that? This is delta H of vaporization. Now, what is occurring in vaporization? We're going from liquid to a gas. Now, let me ask you something. Is that closer together or farther apart? Farther apart. To get things to become farther apart, does energy go in or is energy released? Energy must go in, so this is endothermic, correct? So what is the sign of this? It's got to be positive, so keep that in mind as we go throughout this. And then it says it's 58.51 kilojoules per mole. And the entropy of vaporization, which is what? Delta S, is 92.92 joules per Kelvin per mole. And then the question is, what is the normal boiling point, which is vaporization, correct? Do you agree that's liquid to gas? What is the boiling point of mercury? Solve that. Boiling point. What is the boiling point? No. What is the boiling point? It's the temperature at which a substance begins to convert from a liquid to a gas. So you're solving for T. All right, so hopefully you don't need this, but if you do, that's awesome. We've established that we're solving for T, which is positive or negative delta H over S. Now, you've already told me that T was positive, right? Okay. But what is the value for T? Or excuse me, for delta H? 58.51. And it tells you that it is kilojoules per mole. And then delta S is what? Why does it say negative? Hold on, whoa. We need to talk about this then. That's my fault. All right, so vaporization. You just told me that's liquid to a gas. Is that getting closer together or farther apart? That's closer together. So is that more order or more disorder? That's farther apart. That's what I said. Okay, my bad. So let's start that again. Liquid to gas. Closer together or farther apart? Farther apart. Is that more order or more disorder? More disorder. Positive or negative? Positive. Very good. That's my fault. I fudged that. So it's positive. What was it again? 92.92. And then it tells you it's joules per Kelvin times mole. And here's the situation. I heard someone say it. And I guarantee you, if you divided that out right, congratulations, you get it wrong. You earn no credit for this. And I've told you this for a long time now, that they do this when it comes to doing the delta S and delta H. I don't know why they do it, but they do it. It really is. It's just to see if you're paying attention to what's going on. So people like Mitchell and Nick that don't ever include their units are really going to mess this up. Okay? As long as you get it right, that's fine. But the problem is you've got to pay attention to your units here. Now, personally, which one would you convert? I would convert from kilojoules to joules. So it's not 58. It's 58,000. Thank you. So we're going to convert this to 58,510 joules per mole over 92.92 joules per Kelvin times mole. Now, let's talk about units for a second. What units are going to cancel? So we've got joules and moles canceling, but here's the weird part. What we're left with is 1 over 1 over Kelvin. So how do you get a fraction off the bottom? Multiply it by the reciprocal. So when you take, and it's 1 times K over 1, it's just K. So that's why Kelvin is left. So does that make sense? All right, look. This is the divider sign. So it's 1 divided by 1 over Kelvin. So what I did is I took this number and multiplied it by the numerator by its reciprocal. Are you with me? Because I needed to isolate K. You don't have to show this. As long as you know Kelvin's your unit, rock on. Yeah, as long as you know that that's your unit. But I want to show you algebra why that is your unit. Okay? Yes. Go. Now, so what would you come up with the answer to be? Anybody? Whoa. What? Is that what would you? Did you get 629? Okay. 629 Kelvin. That's fine. It's 6 and 1/2 a dozen the other. You can have a negative boiling point. Think about that. Are there some things that are never, ever, ever a liquid or solid? Oxygen gas. All right, oxygen gas, right? You never see it as a solid. That means it's always in its gaseous state, correct? That means that the boiling point, which makes it become a gas, is above freezing. Because think about it, if it froze, all the oxygen in the air would turn into a solid. So you can have a negative boiling point. Now, let me retract. Let me make sure that I clarify this, Peyton. Can it be a negative boiling point on the Kelvin scale? No, because 0 Kelvin is absolute 0. You can have a negative boiling point on the Celsius and Fahrenheit scale. So again, I apologize for saying that we're both kind of right in a weird way, and that's why units are so important. Yeah. Okay. But does that make sense though? Okay. All right. So the summary on entropy. Delta S, when it's positive, it's more disordered. Devin, you need to hear this. When it's negative, it's more ordered. Okay. Whether a reaction will occur spontaneous may be determined by looking at the delta S of the universe. Again, if it's positive, it's spontaneous. If it's not, or if it's negative, then it's non-spontaneous. Consider 2 hydrogen. Let me ask you this real quick. Why is this reaction negative delta S? Okay, you're going from 3 moles of a gas to 1 mole of a gas. So that's why it's becoming more ordered, so it's negative. The entropy declines mainly due to 3 moles of a gas. Why does that say 2 moles? Is it not balanced, right? It sure isn't. How about that? That's a typo. Do me a favor and add a 2 right there, please. Because when I said 3 to 1, I said that doesn't sound right. So 3 to 2, which is more condensed and less dispersed. To confirm, we need to know the entropy of the surroundings. No, that's not true. And here's why. Let me make a connection real quick. Do you remember a long time ago we said that delta H and Q are the same when you're at a constant volume and a constant pressure, right? So right there where it says Q the surroundings, basically we're just going to plug in delta H of the system. So when you look at it, this is exactly what we just had on the last slide. Come on, get back to it. I'm trying to think of the best way to explain all this. Because here's the part right here that throws everyone off. If you understand that, help me figure out how to explain it. I know what's going on. I'm just trying to figure out how to explain it so everyone understands it. Because if the delta H of the system is negative 483, then the delta H of the surroundings is positive 483. All right, here. This should make sense. If delta H of the system, now what is the system? Very good. Say that again. It is the reaction. If the reaction is exothermic, what's the sign of delta H? So do you agree that this is exothermic? So what is this reaction doing in terms of energy? It's giving it off. Well, what is there to receive that energy? The surroundings. Well, if the system is giving energy off, which is exo, then the surroundings must be there to receive that energy. So how are, in terms of energy transfer, system versus surroundings related? Equal but opposite. And so if you notice, look right here. We've got a negative exothermic, but it's equal but opposite. Okay? So then when we solve for the delta H of the surroundings, we can solve, or once we have the delta H of the surroundings, we can solve for delta S, which is exactly what we just did. This is the exact same formula you guys just used, delta H over T, which gives you that number right there. See, I hate all this. This is the part where it gets really bogged down, and it doesn't make any sense. Yeah, let's stop here because